We're in chapter 11 on Venn diagrams. I redid this chapter. I sent you the information that I had in the new copy. I felt that the Venn diagrams are used in all three areas, and I only covered one of them very well. And so I added some more material in and deleted one piece of material out that was duplicate. Right? The Venn diagrams were come up with by John Venn, a logician mathematician, in about 1880, published a treatise on this. They weren't called Venn diagrams, but at this time he didn't call them by his own name. Later, the name was given by other people to his invention. He was applying diagrams, geometric shapes, various shapes. They're not all circles. They're going to be circles in our volume, but they weren't all circles. And he applied it to logical propositions. He set it up originally to deal with Boolean expressions. And so Hurley wrote in pages 211 and 12, he wrote concerning Venn diagrams with categorical propositions. And I'm going to read what he wrote. Unless an exception is made to the contrary, categorical propositions represented in Venn diagrams are given by the Boolean or given the Boolean interpretation. All S or P means no members of S are outside circle P, and I'm going to use circles here, okay, outside P. No S or P or no members of S are inside P. Now we'll show this in just a moment. Some S or P, and at least one S exists, and that S is a P. Some S are not P, at least one S exists, and that S is not P, not a P. Now, we're taking the existential view. Now, that's not existential. The existential view means that we're dealing with things that actually exist. So when you say at least one S exists, it really does exist. When I'm talking about fairies or leprechauns or stuff like that, of Santa Claus. So we say at least one exists. Each proposition is represented by one of two marks. There's a single mark and a pair of overlapping circles here. And the circles are used by our author here that we're citing, and that, of course, is Hurley, pages 211 and 212. So he's going to use overlapping circles. Now, be aware that sometimes when it gets more complicated, they use other diagrams such as ellipses and other diagrams. You can search this on the internet. We're not going to get as complicated as they can get with it. And I'll show you why. We're going to take propositions that are simple enough that we can do it with no more than three circles. Okay? Each proposition is represented by a single mark in a pair of overlapping circles. That's what he's going to have. He's looking at these four propositions: all S or P, no S or P, some S or P, some S or not P, those four propositions. And that's our four forms. That covers all propositions that can be worded in one of these four forms. So we have two kinds of marks, and he's using a shading area. And if you had mathematics, they use a little bit different version of it. I have that in footnote number 66. Shading an area means the shaded area is empty. And so you'll find that mathematics text is just basically the reverse of it, or at least in some texts. And if we're dealing with an area that's basically an axis, at least one thing exists in that area. The X may be thought of as representing that one thing, that one mark. All right. Now, you don't have to use an X. You could use a star or some other symbol, okay? Just to represent it. Nothing is known about the area. If the area doesn't have anything marked in it, you don't know anything about it. It may or may not be empty. Shading is always used in connection with universal propositions, and placing an X or some symbol like an X, could be a star or something else, connected with particular propositions. So the universal propositions, all S or P, we use a shading here. So what that means is there's not any S's over here in this shaded area. If there are any S's, they'll be right in this football-shaped region in the middle. American football, if someone's listening to this outside the United States. American football is shaped like this right here where my mouse is moving around. And so shading is always used with the universal proposition. That would be all S or P or no S or P. And the content of 4 types of propositions represented as follows. An X is used with particular propositions, some S or P and some S or not P, those 2 propositions. So no S or P means there's not any S's that are in this football-shaped circle because it's shaded. And so, again, these 2 can't both be true, okay? You can't say no S or P and all S or P at the same time, okay? And they're contradictory. They're contrary to one another, I should say. A star is used in the square of opposition chart in this volume. And that's my point. We'll get to our chart a little bit later. Some SRP, and I'm using an X here because that's what is used by our author that we're quoting. So what's he saying? There's an S that exists and it's inside this football-shaped region right in here, American football. And so there's at least one S and it's in this region. Not saying they're not. It's not saying because we don't have anything over here or over here. We're not saying that the only place S's are is in this region. There could be S's over here. There may or may not be. There may or may not be some P's over in this region over here, but where my mouse is moving around. So we're saying may or may not be because there's nothing said about it. If there's nothing in it there, we can't say anything about it. This whole circle here represents S. Now in this case, some S are not P. So we have S and P overlap in this American football shaped region in the middle. And we're saying some S are not P. There's some S's right over in this region right here. There's some that are. We're not saying that there are not any here in this region. We're just saying some S are not P. There's some that are in this region that's not inside the P circle. So we don't know what we have here in this region. Inside that P circle, we don't know what is there. We're not saying anything about what's there. Any questions?
Could you use the example of course, we may be committing equivocation here since there's different kinds of works mentioned in the Bible. So you couldn't put some works are associated with salvation, some works are not associated with salvation because there's different kinds of works.
Yes, so you couldn't put it in here because you're using works in 2 different ways.
Mm-hmm. That's what I was thought.
Oh. Right. Now, that gets those 4 propositions. That's what he's telling us here. Now we come down to the Venn diagrams with the square of opposition chart. And so right here, all S are in. So right here, every S, all S's are inside this circle. There are not any S's over in this region over here, like a crescent moon shaped region that's shaded blue here. They're not in there. And any S's you have are right in this region right here. Okay. No S's are in. There's not any S's inside this circle over here. And if we take the existential view that there's S that exists, and we're saying there is at least one over here. Okay, that's what we're saying. All right, so that gives us a better feel for our square of opposition chart. Now then, some S are in. We're saying that there's an S, at least one S exists, and it's inside this football-shaped region. We're not saying anything about whether or not there's an S over here, may or may not be. We're not saying whether or not there's an N over here, there may or may not be. Same thing with this. Some S are not in. We're saying there's some S, that there's at least one S over in this crescent moon region. And we're saying that's not inside that in circle. This circle over here represents N. And I've used S and N instead of S and P because of S is sufficient, N is necessary. That's just a memory hook for remembering. It doesn't matter what the symbols are. P and Q is was used quite a lot, and that's what remembering mind your P's and Q's. You got to get them right, and you got to put them in the right position. That's where that expression comes from. Any question about our square of opposition chart now? We got it laid out, and I explained every part of it, I think, by now. All right. Now we have another use of Venn diagrams. The ones we used before was categorical, all S or N, and some no S or N, some S or N, some S or not N. Okay. Now Jurgensen and Brown, they discuss conditional syllogisms, conditional propositions. So they use a Venn diagram to represent a conditional. Now remember this: when I quote something, if it has normal print and I bold it, I'll tell you that I did. So this was bold print in the original book. Right? We use a Venn diagram to represent a conditional. That's an if-then statement. Since any point inside circle P is also inside circle Q, now this is going to be the circles down here below us. This diagram represents if P then Q. Similarly, he says the point is not inside circle Q, then it isn't inside circle P. Therefore, the same diagram also represents if not Q, then not P. So he's telling us now. We notice that if not Q, then not P is the contrapositive or contraposition or transposition of if P then Q. So what they're saying is the contrapositive and the conditional in this contrapositive are both true or both false. In other words, they're logically equivalent statements. And so we can prove it with a Venn diagram. So right here, if P then Q, here's your P circle, here's your Q circle. I'm probably going to come here and make these lines heavier in there when I get it finished. Redo that. Okay, so I'll probably do that. Those lines are not heavy enough. Here's your P circle. If P then Q. If it's P circle, it's inside the Q circle. If it's not a Q, then it can't be inside the P circle. If it's not inside this big circle, it can't be inside the little circle. So that's where your conditional and contrapositive are logically equivalent. We've proven it with the Venn diagram. And of course, it can be proven with other means as well. Question there? All right. Now, I put these to the right. We have another one down here. We can see the diagram below us now. Since conditional, the Venn diagram at the right, and that's starting right here, that would be this diagram down here that I've highlighted here. The Venn diagram at the right represents both the converse, if Q, then P, and the inverse of that, of it, if not P, then not Q, right? Therefore, the converse and inverse of a conditional are logically equivalent statements. I'm not going to be using converses and inverses too much, okay? I believe they're useful, but I've been using contrapositive and transposition primarily, okay? We're going to make application of Venn diagrams to the plan of salvation here, for example. If one is saved, then he has been baptized, 1 Peter 3:21. It's depicted by this following Venn diagram, if P then Q. If one is saved, P circle, then he's been baptized, that's the Q circle. There are people who are baptized but not saved. We can prove that. We can give proof of that. And so that would not be the case. Even our Baptist friends would agree with that. They would say Mormons are baptized and Jehovah's Witnesses are baptized, and there are even some pagans who baptize people. And so that wouldn't necessarily prove that they're saved, because they wouldn't even believe. And so they would agree that one has to believe in order to be saved. So yes, If you're inside the saved circle, the P circle, you're definitely inside the circle of those who have been baptized. That's what that's saying. All those who are saved are inside the circle Q, which represents those who have been baptized. That's exactly what the Bible teaches. Comments or questions? So it also represents a contrapositive. If one is not baptized, then he has not been saved. Let's look at it. If the P is the saved circle and the Q is the baptized circle, he's not inside the Q circle, he can't be inside the P circle. So if he hasn't been baptized, then he's not saved. Again, that fits in with our proof regarding we use another theorem, De Morgan's theorem, to prove that from Mark 16, 15, 16. Any questions? All right. Venn diagrams relating to the dispensations. Let's look at the dispensations. We have 3 dispensations. Now this brings us to have, let's go back to this diagram before I get away from it. I want to look at it here. We have either it's true or not true, okay? So that makes 2 options. We have 2 variables with 2 options. That would be 2 to the second power, or that would be 4 possible conditions, 4 situations. We could have he's saved or not saved, he's baptized or not baptized. So right here, he's either inside this circle or he's not. Okay. He could be inside this circle and he would have to be baptized. All right. If he's outside this circle, he could be out here and he could be baptized but not saved. Or he could be out here, he could be not even baptized and certainly not saved. So he's got 4 possibilities. So this here twice, and then here twice, out here or in here. And so we have 4 options. So you take the number of variables and raise it to the 2 power because you got either yes or no. So 2 to the 2 power, 2 squared is 4. 2 times 2 is 4, that's 2 squared. Now then we come down here, we got 3 options. We have our dispensations, 3 dispensations. So either patriarchal or not the patriarchal, Mosaic or not the Mosaic, Christian or not the Christian. And so we got 3 variables and we got 2 options for each. 3 to the 2, we have 8 possible situations that can occur. Does that make sense? Everyone got me? All right. And we could have someone who's on some law that's under the patriarchal law, but not under the Mosaic or Christian dispensation. Some situation, some law or commandment or requirement. All right. And I deal with this in a series of lectures on this. We can come down, that's one option. We can come down here, this red one right here where my mouse is, that's your second option. Inside this, but not inside these over here. Over here, just Christian only. That's 3. We can get inside this circle where it's patriarchal and Christian both. We get inside this circle where it's patriarchal and Mosaic both. So that's, we got 1, 2, 3, 4, 5, and then we got Mosaic and Christian, that's 6. 1, 2, 3, 4, 5, 6. All right. Then 7 would be all of them, all 3 of them in this region right in here. It's almost a triangle, but it's bent a little bit. It's a little bit circular. Looks a little bit like a triangle. Right in the middle, that would be all 3 dispensations. Okay, that's 7. The 8th one would be outside out here where the white area is. That's 8. So we got 8 options. If you try to get 4 variables, it's hard. You can't put 3 circles together, 4 circles together and make them overlap right. Can't be done. You have to do it with something besides a circle. So it gets a little more complicated. But we don't have any situation we're going to be using more than 3 variables for our purposes. If you get into it, you can study it out for yourself. But it's pretty cool, the method. They have some diagrams that are very interesting. You just do this. You can Google it and look at some of the diagrams they come up with. Okay, But for our purposes, we're just going to take three variables. We got three dispensations. Any questions? Look here. There's the patriarchal dispensation, just that region, the blue region. Here is the patriarchal and Christian where they overlap between the two. There are things in the patriarchal and Christian dispensation that they both have that the Mosaic didn't have. Let me illustrate. What's one thing? Well, the patriarchal or the Christian observed the Sabbath, but the Mosaic did. Okay? Mosaic observing the Sabbath over here, and the other ones weren't. So that would be Sabbath observance. Okay? There are other things, but we can show them here. So that's patriarchal, that's two. Come down here. We have timeless things that would be all three dispensations have it, and I believe we can prove it. Thou shalt not kill, not murder, and steal, and so forth. And so we can get a number of things that are in all three dispensations. And I have a series of lessons there on the internet where I deal with all of this. So that's where all three of them right there. Right here is the patriarchal and Mosaic. Well, what would be in that? Well, that would be animal sacrifices, for example. Both of them had animal sacrifices. We don't have animal sacrifice in the Christian dispensation. So that would be here, but it wouldn't be here or here or here. But it would be right here. These two together, both of them had that in common. Right? Here's a patriarchal Mosaic. This is strictly Mosaic. What did they have? Well, we have Sabbath keeping. There's other things they had. We had a priesthood that was different, a tribal priesthood. So there's several other things that are strictly Mosaic. Okay? All right, the Mosaic dispensation. Right here is a patriarchal and Christian, and we've already laid that out. And here's the Mosaic and Christian. I had a hard time finding anything that would be Mosaic and Christian. And I found some things that both were together in, but that was a hard one to come up with anything. Now, right here is strictly New Testament, baptism. So we didn't have a number of things that's strictly for us, okay?
Lord's Supper.
Lord's Supper would be another one. And so there are several things. The name Christian is even a New Testament term. Okay, so we can have a number of things, and I have these laid out in these sermons. These Venn diagrams are taken from my lectures on the patriarchal law, and I'll lay it out right down here. And this is a link to it, and you have that. You can click on that and go to that link, and there's about 21 or 22 or something like that lessons that'll lay it all out. And I show that every principle of morality is in all three dispensations, and I believe I prove it, logically prove it. Okay? Now, we have another one down here. It's a Venn diagram from my Role of Women book. Here are the page numbers in it. We have didascal type teaching. That's the teaching of 1 Timothy chapter 2, verses 11 and 12, particularly verse 12. And we have that type teaching. Then we have action X. Action X, if you look at it here, represents asking questions, imparting information, and so forth. Now, can a woman impart information to a man? I believe she can. But there's some ways she can impart information to him. So the didascal type teaching, it's forbidden in 1 Timothy 2:12, would include such things as preaching, teaching, imparting information by preaching and teaching in a Bible class situation or something like that. That's an authoritative act. And we would agree that a woman could give a man a Bible tract. That would be impart information to him. But we would probably, most of us would agree that she couldn't stand in the pulpit in a mixed assembly on Sunday morning and preach. And if we do that, then we have to say that there's some actions of imparting information over here that are not inside the didascal type teaching that's forbidden in 1 Timothy 2:12. This is forbidden, And this is not forbidden over here by a woman. Give him a tract and the Bible correspondence course out to him. Get him a Bible, something like that. And so there's a number of things. And then she could impart information by that means, but she couldn't impart information if this included preaching from the pulpit on Sunday morning or something to that effect. So most brethren would see that. I don't understand why they can't see this. And that's a Venn diagram. Is there any question about that? But I discussed all of this on this chart. It's in that book, and I used it here. When I debated MacDonald, I dealt with that and used this chart in that debate. Okay. Any question? That concludes that chapter. And we have enough time to go into chapter 12. Chapter 12 is a different kind of reasoning now. Deductive reasoning, we take a universal conclusion and we draw particular applications to it. All those who are saved are those who are baptized. John Doe is one who is saved. We conclude John Doe, a particular person, has been baptized. So that's a deductive reasoning. Inductive reasoning goes from the particular specific case to the general case. So it goes the other direction. Inductive logic only demonstrates that a matter is likely to be true or probable. Bertrand Russell claimed that it's not related to probability, but I think Bertrand Russell actually had two subdivisions of inductive reasoning, inductive logic. I think what he did is he had the general knowledge of induction, something that's only generally known to be true or thought to be true, and then that which has mathematical relationship, mathematical probability, which we'll get into a little more detail in a couple of the appendixes. Right? So I think Russell may have had two categories. It doesn't really matter. Russell was an atheist, and he had some real good logic, but when he starts applying it, he didn't apply it very well. He made some pretty bad errors in his reasoning power, when he tried to argue for atheism. Inductions cannot determine the extent of the mathematical probability unless total number of possibilities is known. That gets into appendixes K and Q. Right? But it can disprove a matter. Now I'm going to go back. To this. I want you to see how it can disprove a matter. We'll come back up here. I'll come back to this in just a minute. Right here. We have a conclusion. Now, induction makes an argument from particular, and it argues from this, and something is true, some S or N, then we argue back up here. There's a likelihood that all S are N. So, and that would be true, or it could be true, but it could be falsified by just finding one S that's not N. Does that make sense? All polar bears are white. So we look at one polar bear and he's white, and you say, oh, maybe all polar bears are white. And so we come across here and look at another polar bear, it's white. And say, oh, yeah, well, we got some more. You look at 24 polar bears, they're all white. We get to thinking, well, maybe all polar bears are white. We come across a polar bear that's black, we say, oops, that disproved it. So it just takes one thing to disprove it, to contradict it. That gets back to your square of opposition. That's what we were talking about. Let's come back over here to it now. We can see what I'm talking about here. We're gonna go through this when we get it here. Induction can disprove a matter. And so we can say all S are N, that is disproved by some S's are not N's, okay? Just one S is not N. Just take one, and that automatically disproves the whole inductive process, right? So that's how it's accomplished. Now, Copey, I think Copey was British, but they spelled premises with two S's. But I found one book, and I can't find, but I only found one book that had this. It was a link on the internet that claimed that this was actually a little bit different meaning than a premise with a single S. I can't find any more, and I'm just going to say that's a possibility. But right here, an inductive argument, on the other hand, involves the claim that not that the premises give conclusive grounds for the truth of the conclusion, only provides some support for it. Now, that's inductive, see? It doesn't conclude that it is. Now, deductive reasoning, you say all S or P. If that is true, then some S or P, or one S is P. And so we can draw a conclusion that if the premises are true, and it's valid reasoning, then it's got to be true. The conclusion has to be true. That is necessarily true. That's a necessary inference. Okay. So inductive arguments are not valid or invalid. We don't use the word validity to them. We use another term, so we'll come to it later. Okay. So we don't use the words valid or invalid with inductive arguments. Not in the sense that we do with deductive arguments. They may be evaluated as better or worse, depending on the strength of the support provided by their premises, but that is by the degree of likelihood or probability that premises confer upon their conclusions. If you look at two polar bears and they're both white, and you say, well, probably all polar bears are white, that's not very strong evidence. But if you look at 2,000 polar bears and they're all white, and you get thinking, well, there's maybe only 20,000 polar bears in the whole world. We got a pretty good sample of them. We looked at them in Greenland. We looked at them in northern Russia. We looked at them in Alaska and northern Canada. We say, they're probably all white. Okay. And we sample them everywhere. So that gets into the rules for statistics as well. So we have to apply some rules, statistical principles. Martin and Ullman, this is a real good book. It's very readable, and it doesn't get too highly technical. So this book, if you can find it, is real good. It could be studied, and you don't have to have a bunch of math background and everything. It's very readable, very, very useful book. It's used for people who are studying logic and rhetoric of exposition, and it's primarily for speech teachers. Or people studying to be speakers. It is time to offer a definition of Martin Ullman said, an inductive proof is one that moves either from a group of assertions about some events, things, or situations of a certain class to assertion about all such events, things, or situations of that class. See? From assertions, or B, from assertions about miscellaneous things and events to assertion that explains them in a relatively simple way. So it's two possibilities, and that's types A and B. But then he turns around and says that actually these overlap. They belong together in one definition. Was type A is a variety of type B, as he's saying. That's a little harder to see that, and I won't go into it, but what I'm saying here is he's kind of explaining what we have, generalizations or special cases of type E and type B explanations. He goes on and says, let's go on and say, James, you got something to add? Go ahead and add it, if you would, please. Something there?
No, sir, I'm good.
Okay. As will become increasingly clear, the definition cuts corners, he says. But he says this will work and explains primarily. Inductive reasoning is a little bit broader than deductive reasoning. Bruton and Peterson they'll talk about it, and this is a high school level English book from back about 50 years ago, but it's pretty old. Reasoning is a process in which the mind arrives at conclusion by examining experience by picking out a pattern of regularity. That's pretty good definition. There are two methods, and that's inductive and deductive. And he says that's important that you understand both of these. If you're going to read and if you're going to write, you need to do that. he goes down here with inductive reasoning and explains it. And he uses a fellow who has a good last name, H. Monroe Fox. And he has this very interesting situation. I'll just give a summary of it. He has this table in the garden, and he puts a watch glass on top of the table, but puts it on the top of a blue cardboard. And in place this watch glass, puts a drop of syrup in it. After a while, bees come and disturb it, suck up some of it, take it back to their hive. And then the bees somehow communicate it to other bees, and other bees start coming, getting syrup. Okay? And so they do this for a while, and then they move the card over a little bit and add a red card over on the other side. They don't put anything where the card was. They move the card over a little bit with the card. They put this watch glass on both cards, on a red card and a blue card, and they have nothing on the card, no honey, no syrup. And the bees come back and they come to the blue card. They don't go to the red card. And so they don't, but they don't have anything there. There's no syrup on it. So they arrive, they only go to the blue cards. They don't go to the red card. So he concludes that bees probably can tell different colors. That's his conclusion. Pretty good conclusion. Now, when I studied techniques for research techniques in graduate school, and we studied what we needed to change variables. For instance, they put the red and blue card at different locations, and each had an empty watch glass on it, on both of them. What they should have done is, once they did that, they should have done this process again and put the red card where the original blue card had been with no syrup on it, move the blue card over. That would have gotten another variable that they could have measured. So you can change your variables rather than run the procedure again. And so they could have ruled out some other possibilities. But this was a very elementary situation. And there's other things they could have done, but yeah, I think it was pretty good. And as for high school students, it was a pretty good illustration of inductive reasoning. So what he claims that the bees, in all likelihood, they can tell blue from red. And it wasn't the location of where it was the actual color of the card. Now, what I'm saying is, if he'd have put the red card where the blue card was, and in a second experiment, repeated it, but put the red card where the blue card was with a watch glass on it, and then put the blue one over where it was the other time, or maybe even moved it somewhere else on the other side where the red was. He could have repeated this process 2 or 3 times, and he would have ruled out some other possibilities. But this was a pretty good setup, elementary but pretty good. So he's observing the specific behavior of bees, and so he used the principle of regularity, and in this case, consistent behavior of the bees. And the assumption, the principle is general operation. So this reasoning is what's done in science. And of course, it'd be in scientific experiment, would be much more rigorous than that. Okay, they'd change different variables and do it again, repeat it over and over. In science, true science, they got to replicate it again and again, and so that there was not something else involved in it. Okay, and there's 3 basic errors that he has that can get into the 3 most common errors in reasoning. A generalization not based on sufficient number of instances. He didn't repeat it and change other variables, okay? And the instances chosen aren't typical. The exceptions to the generalization are not explained. Sometimes there'll be exceptions to it. An exception will come out, and it needs to be explained, okay? That's what he tells us here. Any question, that's out of this book. This is a an English grammar book from high school all back in around 1970, somewhere about when that came out, close to 50 years ago. Okay. You get the bibliography and see when it was published. All right? Questions? It's the basis of the scientific method. The scientific method follows the form first. Now, this is ideally what the scientific method should follow, the form it should follow. They should observe a phenomena, form a hypothesis. It's an A-type proposition. Explain the phenomenon, and third, they develop a system to test the hypothesis. So that's what they should do. If the hypothesis violates a law of science, it must be discarded, and a new hypothesis must be formed, or the validity of the law of science must be challenged. All right? And one of these has to occur if they follow it rigorously. The hypothesis is wrong in one single instance, an O-type proposition, and it's disproven. We go back to square of opposition and see that, because we're really affirming an A-type proposition. We have an O-type proposition of the same substance, and it would negate it or contradict it, okay? Unfortunately, you can go to Appendix B and you can see that there's a bunch of scientists, and these are really reputable scientists, that did not follow this in a study that was done. This was with NASA people. It's very illuminating, very eye-opening. Appendix B, I discuss this. I cite some studies. These were people working for NASA. All right. The scientific method, I developed it very extensively in my Biblical Flood book. I'm not going to spend a lot of time on it in this. I'll do some, but not as thoroughly as I might could. And I've done this already in that book. The instance where it's absolutely certain that inductive logic has proven a matter. Now, it could be certain if we had one who was reasoning and he was omniscient, that would be deity, or has every fact concerning the matter. All right, with either omniscience or knowledge of every fact, one to reason in a deductive manner. Now, we're going to claim that the scriptures contain the universe of information on man's salvation. So, that being the case, reasoning inductive. Let's see what the word universe means. Here's Merriam-Webster. A set that contains all elements relevant to a particular discussion or problem. That's Merriam-Webster's Collegiate Dictionary. You can type Merriam-Webster's dictionary on the internet and Google it and find it and get it free, okay? You just look this definition up. So all of the relevant information, if we have the scriptures, if they contain all the information that's needed for man's salvation, and we put all of the scriptures together, then we can reason inductively from it and wind up, if we got all the information, we will actually wind up reasoning deductively from it. All right? Now, if we go through this process, like the scientific method in studying the Bible, what we would do is we would find a verse that says man has to believe to be saved, for example. We say, okay, now I know that he has to believe to be saved. That verse tells me. We'd say, okay, what does the other verses say? We find another verse that says, well, he has to repent to be saved. And you say, well, that when they're logically evaluated, those two don't contradict one another. It should just be another requirement. So we say, okay, now we got two requirements. We just keep going and we wind up with the plan of salvation. And as when we get through the whole New Testament, we'll have a pattern for salvation that we know is we can reason deductively from, because we've taken all the universe of information about salvation, put them together. And that's why we had to do that. Now, we have to be honest enough to, whenever we draw a conclusion, we may, if we see the man has to believe, we say, well, that's all he has to do. Well, maybe not. So we have to say, I'm going to be honest enough that I'm going to look at it and see if there's other things required. It doesn't say faith only. If we go to James 2, we can say faith only does not save us, can't be justified by faith only. We understand justification is what will occur when one is saved. He's justified. And does that make sense? Any questions about that or comments? Okay. Let's go further in this then. We have the nature of truth. We'll come back to it just in a minute. Pragmatists, and this is what's taught in colleges of education in the United States. And I've been there, done that. Okay, I've seen it. And pragmatism is what's taught. And truth learned by the scientific method is tentative. They admit it's tentative. So there's two kinds of truth. There's tentative truth and absolute truth. And we'll lay it out and explain what I mean by that. Pragmatism holds there's no absolute right or wrong. Here's a quote. Philosophically, pragmatism departs from traditionalist approaches in holding no particular absolutes, no eternal values, no a priori truths. This is G. Lee. There's two, I had cited two people's named Lee, so I had to have the first initial, 1957. So he's laying out for us what the pragmatist teaches. Now, pragmatism is the philosophy of education that's taught in most colleges of education in the United States. Not all of them, but most of them teach that's what they teach. So there's no absolute right and wrong. There's no eternal values. Pragmatism is the basic philosophical system taught in most colleges of education. School teachers in the United States of America are taught this philosophy. Now, here is the American Journal of Physics article cited, and I call it committee. It's a committee of physicists that made this statement. No scientific theory, no matter how strongly supported by available evidence, is final and unchallengeable. Any good theory is always exposed to the possibility of being overthrown by new observational evidence. What they're telling you is that there's no scientific theory that is absolutely certain that we're certain is true. No matter how strongly supported. That's a very amazing thing to assert. And that's true. That's exactly true. Because it's all inductive reasoning. Okay? John Coley, this is out of a physics book that I have. And although the testing of theories can be considered to distinguish science from other creative fields, it should not be assumed that theory is proved by testing. Okay? And he gives, first of all, no measuring instrument is perfect, so exact confirmation is not possible. If you've ever studied any at all, you know the measuring instruments themselves affect your measurement. If you're measuring the temperature, so we stick a thermometer in it, the thermometer sucks some of the energy, some of the heat out of it to warm up the thermometer. So that's very simple right there, illustration of it. So it's not possible to test a theory in every single possible circumstance as well. So a theory is never absolutely verified. In fact, theories themselves are generally not perfect. He goes on and tells us rarely agrees with the experiment exactly. So there's always some overlapping. Doesn't totally agree with it within experimental error. In every single case which is tested, it just doesn't always do it. Something happens, something's different. And so your measurements don't always come out exactly like you predicted. And there'll be some tolerance in it. And he talks about the history of science, says process of one theory replaces another. Indeed, the history of science, theories come and go, and long-haired theories are replaced by new ones. He goes on in this last paragraph down here, and he tells us that the new theory is accepted by scientists in some cases because its predictions are quantitatively in much better agreement with experiment than those of an older theory. But he said, but in many cases, the new theory is accepted only if it explains a greater range of phenomena than does the older one. So again, they'll hold on to a theory that they've got evidence is not true because it's the best they've got with their beginning premises, see? And that's important to remember, right? J. Lee, this is another Lee, he says, because all scientific statements must be considered as best only tentatively correct, The phrase scientific proof should be used with extreme caution in scientific discussion. Strictly speaking, nothing in science is truly proved. That's amazing, isn't it? We hear scientists saying over and over, well, we're absolutely true, that certain of this. Well, we have degrees of certainty, what we've run into. Now, there are some things that have been bored out over and over and over, and they work. Airplane wing gives lift, Bernoulli principle, and it's a pretty well known how it operates. And planes fly every day, and it works. And we have other things that work, but there may be some situation where the airplane wing doesn't work. We just hadn't found it. And maybe some planes crash and we haven't found out that there's something that's happened. And so that could happen. I think we could get something that, like icing on the wings or things like that, would change the shape of the wing. Of course, that would not mean that the principle itself was wrong. So there might be something that we don't even know about, that we hadn't ever encountered or still could possibly true. But I trust the Bernoulli principle, and I fly. I'm not afraid of it. Kolbe goes ahead and says the pattern of indirect testing or indirect verification consists of two parts. First, you deduce from a proposition to be tested one or more propositions which are capable of being tested directly. It's not science if you don't have a hypothesis that can be tested. If it can't be tested, it's not verifiable. It's not science. It's nothing but a hypothesis. It's a theory. It's an idea, hypothesis that you have. Now, they use the terms theory, hypothesis, and law in different ways. So it's basically a hypothesis. Then the conclusions are tested and found to be either true or false. Now, that's the ideal case. If the conclusions are false, any proposition implies it must be false also. When Kolbe is working as a logician, and that's true. But you see, in the real world, sometimes a man will be called a scientist, and he may have an axe to grind. He may want to prove something, and he'll ignore the evidence. That does happen. That's in Appendix V. You can go to Appendix V and see it occurring, and it's documented in the test, in studies that were done. Right? If the conclusions are false, any proposition implies it must be false also. Kolbe is absolutely right. If the conclusions are true, this provides evidence of truth. The proposition being tested, which is confirmed indirectly. Now then, if the conclusions are true, we just say the probability is higher that it's true. We haven't proven it. We don't prove necessarily. We give stronger evidence for it. The evidence becomes stronger. Should be noted, the indirect testing is never demonstrative or certain. That's what he tells you there. Now then, here's another one we cite, and I'll get who that is. This is Kolbe again. Again, he says in a different part of his book, few propositions of science are directly verifiable as true. They're just not true. We cannot verify most propositions directly. We have to do it indirectly. None of the important ones are, he says. Every explanation is put forth tentatively and provisionally. Any proposed explanation regarded as a mere hypothesis, more or less probable on the basis of available facts or relevant evidence. So we're dealing with probabilities. As I said, the airplane wing, it works, and we've shown it over and over and over that it works. And we see birds flying. We know something has to happen. There's some law there, some law of physics that would explain it. The vocabulary of hypothesis, theory, and law is unfortunate, he says, because it obscures the important fact that general propositions of science are regarded as hypotheses, never as dogmas. But you get into organic evolution, some of the atheistic views that have to occur, they get pretty dogmatic about it. The hypothesis question of truth falsehood is open, and there is, he said, but really there should be a continual search for more and more evidence to decide the question. Here now, I want you to see what he determines as evidence is used here refers only to experience. Sensible evidence is the ultimate court of appeal in verifying scientific propositions. Science is empirical. Empirical means you've got to verify it with one of your five senses, one or more of your five senses. And holding the sense experience is the test of all its pronouncements. If you cannot test it or observe it, it's not science. The beginning of the universe is not science because you can't test it, you can't observe it. But the beginning of life is not science, not scientifically verified one way or the other, because you can't test it. They have never created life. They have not seen it come into existence, and they can't look at it in the lab. They can't observe it. It's not empirical. And the tests have to be replicated. That's one of the things they require. So right here, all of this talk about science has proven that organic evolution has occurred is a bunch of bunk, because it's not true science by the definition of science. Colby's definition and other people's definition of science. Any question anyone has? The trick is they like to throw the word science around because it sounds so good. Medawar, and I'll go down to my footnote, Medawar was a Nobel Prize winner in physiology of medicine, 1960, and that meant something back then. It doesn't mean much today. Scientific truth, in a sense, I shall describe and explain it below, often thought of as a scientist's work. So asymptote, they're getting into big words that are used in mathematics, which would be a better word. Now, asymptote is like a curve is getting closer to the axis or to some point, but it never reaches. It gets closer and closer the closer you go, but it doesn't ever get there. Okay. And that's what they mean by it. And then he used the big word apodictic. Man, oh man, let's look it up down here. Apodictic. Oh, expressing or of a nature of necessary truth or absolute certainty. See? So when he says there's no apodictic certainty, there's necessary truth, it's not necessarily certain. See, that's a fancy word. And words like that, I have to just footnote them because I had to look them up myself. Sorry about that. I had to look that word up. So I put it in a footnote. No finally conclusive certainty beyond the reach of criticism. There's no substantive goal. There's a direction only, just points you in a certain direction. Now I use another word, ulta thule. I don't know. I've flown over Greenland, but I don't know that I was over Thule, Greenland. But that's another word that's used here. It's the northernmost part of the habitable Earth. Northern the ancient world. It's way up in northern Greenland too. There's an air base there. Okay. Now that's the ultimate of the asymptote of the scientist endeavors the truth. He's getting closer, but he's not there. He never will reach it. That's what he's saying with his methods. Okay. Now, Peirce, Charles Sanders Peirce, a very famous man. He's quoting some men that are very famous and they're atheists. The conclusions of science make no pretense to be more than probable. That's what he says. And Medawar quotes him. Immanuel Kant, he's quoted also, and he quoted on page 41. Hypotheses always remain hypotheses, that is, suppositions with the complete certainty of which we can never attain. Now, these are very important. We're talking about a bunch of men that are atheists or agnostics, and they're admitting this. These are admissions. Right. There's the definition of asymptote right here. Medawar is saying the scientist never reaches absolute, he just gets closer to absolute truth. Right? Abel, an atheist, this is in a book that it is written by atheists, challenging the Bible and challenging God's existence. So you can go and get the name of the book. I have it in my library. He says science is quoting an atheist. Now, on the other hand, while not providing absolute truths, see right there he admits it's not absolute truth. It does find systematic order, develops models that allow us to understand nature and her behavior. We get some models out of it. Well, the method of science, observation, hypothesis, and test leads to new knowledge and deeper understanding. Now, that's true. I use science, and I believe that it's very valuable. He goes on and says most scientists take for granted that these models, at least the extremely well-tested ones, do describe reality. Now, what he does, he cites some things, and they like to call us flat earthers. We're like the flat earth people because we believe in God. They try to put us in that category. The earth really is round, does turn on its axis, does go around the sun. And so that's put in there as a dig. And they claim that we, by believing in God, are in that same category as the flat earth people and the people that says the earth don't rotate on its axis, doesn't go around the sun. See? It's a subtle dig. Then he says this acceptance of science is really a religious one. It's basically a religion. He's admitting it. And if challenged, the same scientists will usually agree that technically no truth can be proven by science to the absolute. But they'll claim we absolutely know that organic evolution occurred, see? Turn right around and make an absolute claim. But they can't do it. Now, my quotes of atheists and agnostics here are what are called ex concessu arguments. An ex concessu argument is one where you quote the person that you're in dispute with, where he agrees with your position or he contradicts himself, okay, one or the other. And that's called an ex concessu argument, okay? Actually, truth is not tentative. I'm claiming it's not tentative, it's absolute. We have is the understanding or knowledge of truth is tentative. All right? I'll illustrate this. We can look at a person and look at him and say, from his facial features, carnival sideshows will do this, people will go in. My father-in-law used to go in and he looked very young. And he would go in and have him to guess his age and had proof of his age. And he could at the carnival shows, they'd guess his age and they wouldn't get it right. They'd be too far off. He'd have him much younger than he really was. And but he looked younger, quite a lot younger, of course. He died in his 80s. So, but he looked much younger than he really was. So that's very interesting. At a carnival show, they look at the physical features and guess the ages, as frequently done. All people have ages that are absolute, but the one guessing the ages looks at the evidence and does not know certain ages. His knowledge of their age is tentative, but their ages are absolute. They still have an absolute age. It's tentative what he thinks their age is. Okay. That claim that truth is tentative and so subject to error, all truth is changeable. That's what they claim. It's tentative. And so minor premise, blank, whatever we put in here is truth. And therefore what we put in here is changeable. All right, let's come down here. Let's see what we put in there. All truth is changeable. The assertion that truth is changeable is truth. The assertion that all truth is changeable is changeable. Well, that contradicts itself. Major premise is false. Contradicts itself, contradictory. And so we get a O-type premise from it. Some truth is not changeable. This appears from the fact that the negation of some sentences and all sentences, okay? From our square of opposition, we see we have proven that some truth is not changeable, right? Because we have a contradiction in this up here. Now, what does science really assume? We're down to about, we're going to quit right here. We're going to look at the assumptions of science next week. Are there any questions? Anybody?